Welcome back to Mechanical Engineering Made Simple. Quick update before we dive in, we've officially launched paid subscriptions. That means if you want deeper cuts, special episodes, and real answers to the questions engineers actually care about, you can now support the show directly. Think of it as buying the creator a cup of coffee 99 cents a month, gets you access to exclusive content, listener-requested breakdowns, and episodes focused on turning engineering skills into real-world leverage, opportunity, and income. Okay, let's get into it. Today we're doing a deep dive on a topic that is, it's completely fundamental but so often invisible: fluid mechanics.
It really is. It governs everything from, the blood flowing in your veins to how a jumbo jet stays in the air.
Absolutely. So I think our mission today should be to kind of cut through that complexity.
I agree. Let's unpack the core ideas: what a fluid actually is, how we try to model its motion even when it's chaotic, and, the practical tools engineers use every day to make sense of it all.
Perfect. So let's start right at the beginning. When we say fluid, what are we really talking about? What's the key difference between, say, water and the air around us?
Well, it really boils down to two key characteristics:
Mhm.
compressibility and viscosity. We usually split them into liquids and gases.
Okay.
A liquid, like water, we generally consider it to be incompressible. It holds its volume and it will form a free surface. A gas, on the other hand, is easy to compress, and it just expands to fill whatever container you put it in.
So for most calculations with water, you can just assume it doesn't shrink under pressure to make the math easier.
That's right, for the most part.
Yeah.
But if you get into really high-pressure systems like heavy industrial hydraulics, that tiny bit of compression starts to matter.
And for gases?
With gases, it's a bit more nuanced. They are definitely compressible, but if the pressure changes are small and the speeds are low, engineers will often treat the flow as if it were incompressible. It's a very useful simplification.
And the other half of that coin is viscosity. I always think of it as, the difference between wading through a pool and trying to run through a vat of honey.
That's a perfect visual. It's that internal friction, the fluid's resistance to flowing. And that one property, viscosity, connects the entire history of the field.
Right, because we tend to think of fluid mechanics as this modern calculus-heavy field, but the practical side of it, hydraulics, is ancient.
It's completely ancient. It was born out of pure necessity. Civilizations needed to move water. We have irrigation canals in Egypt and Mesopotamia that are, over 6,000 years old?
Wow.
And think about the Roman aqueducts. They weren't just amazing structures. They were incredible feats of engineering. They had to calculate the right conduit size, the right slope, all to overcome friction over miles and miles.
But the first person to really start looking at it with a sort of a modern scientific eye was Leonardo da Vinci.
He was a true pioneer. He didn't just build things. He observed everything. He was the first person to really try to visualize flow. His notebooks are filled with these incredible sketches of streamlines and vortices or eddies.
He was basically searching for the most efficient shape, the path of least resistance.
Exactly. He was trying to find the least resistive streamlined shape. He was laying the groundwork for concepts we now need supercomputers to model with CFD.
And that brings us to the mathematical elephant in the room, the Navier-Stokes equations.
Right. The fundamental equations of fluid motion. They were worked out in the 19th century, and they're basically Newton's second law, F equals ma, but applied to a tiny moving piece of fluid.
So if they describe everything, why are they so notoriously difficult to solve? Why do they haunt engineering students?
Because they're nonlinear. And that nonlinearity comes from what we call the convection terms. These are the bits of the equation that describe how the velocity changes from one point to another.
So the fluid is essentially interacting with itself.
That's a great way to put it. The motion of one part of the fluid instantly and chaotically affects all the other parts. That's where turbulence comes from. It's why tiny changes in the starting conditions can lead to wildly different outcomes.
Which is why an exact solution is almost impossible to find in most cases. So how do engineers get around this? How do we simplify?
We use a very powerful shortcut, the Reynolds number.
Okay, tell us about that.
The Reynolds number, or REE, is just a ratio. It's the ratio of the inertia forces, the forces trying to keep the fluid moving, to the viscous forces, which are the frictional forces trying to slow it down.
So by calculating that one number.
By calculating that one number, you know which forces are dominant. And if one is much bigger than the other, you can just drop the smaller term from the Navier-Stokes equations. It cleans up the mass beautifully.
Okay, so let's take the extremes. What if the Reynolds number is very, very small? Viscosity is dominant.
That's a situation we call creeping flow. Think of lava or maybe the oil film in a sliding bearing. Inertia is so small, it's basically negligible, so we just omit the entire inertia part of the equation.
And that simplified version is solvable.
Often, yes, analytically. Now, what about the other end of the spectrum? A huge Reynolds number.
Like the air flowing over a jet wing at high speed.
Perfect example. There, inertia is completely overwhelming viscosity. So we do the opposite. We neglect the viscosity term and treat the fluid as if it were inviscid or frictionless.
But what about that messy middle ground where inertia and viscosity are both important?
Right, and that's most real-world engineering problems. You can't simplify, and that is the domain of computational fluid dynamics, or CFD.
Using computers to do the heavy lifting.
Exactly. We use numerical methods to break the problem into millions of tiny pieces and solve the full equations for each one, step by step. It's the only way to follow that kaleidoscopic change of flow that defines reality.
That intermediate range of Reynolds number also brings us to another key concept people always want to understand: the difference between laminar and turbulent flow.
Yes, this is absolutely fundamental. Laminar flow is smooth, it's orderly. You can picture it as these neat layers of fluid just sliding over each other. It's very efficient.
Low energy loss.
Very low. Turbulent flow, on the other hand, is chaos. It's full of random lateral motions and swirling eddies. It's a mess.
So if laminar is so much more efficient, why don't we just design everything to stay in the laminar regime?
Because to get the performance we need, the speed, the flow rate, we often have to push the velocity up. And that pushes the Reynolds number up right into the turbulent zone. And that turbulence costs you a ton in energy.
How do you even quantify that cost, that chaos?
We measure it with something called shearing stress. In turbulent flow, the total stress has two parts: the normal viscous stress and an extra component called the turbulent shearing stress. And this extra stress is related to something called the Reynolds stress, which is basically a measure of the momentum being violently exchanged between fluid layers by those chaotic eddies.
And this is all happening most intensely right near a surface, which brings us to another huge breakthrough: the boundary layer.
Yes. Ludwig Prandtl's brilliant insight from the early 1900s. He realized that all the important effects of friction are basically confined to a very thin layer right next to a solid surface.
Boundary layer.
The boundary layer. Inside that layer, the velocity goes from zero because the fluid sticks to the wall, the no-slip condition, all the way up to the full free stream velocity, just a tiny distance away.
And this layer isn't static. It changes as it moves along the surface, doesn't it?
It does. It starts off as a nice, smooth, laminar boundary layer at the leading edge. But as it flows downstream, it gets thicker and more unstable. Eventually, it transitions into a chaotic, thick, turbulent boundary layer.
And that transition is bad news for drag.
Very bad news. A turbulent boundary layer creates much, much more skin friction drag than a laminar one.
Now, the power of these dimensionless numbers like Reynolds extends beyond just predicting flow types. It's crucial for design and testing, right? Through dimensional analysis.
It's the engineer's secret weapon. The idea is to group variables into non-dimensional quantities. This lets us summarize tons of experimental data onto a single chart, and more importantly, it lets us achieve dynamic similarity.
Meaning you can test a small model and know it will behave exactly like the full-scale version.
As long as the key dimensionless numbers match. If viscous forces are important, your model's Reynolds number must match the prototype's Reynolds number.
What if other forces are at play, like gravity, for a ship moving through water?
Then you need to match the Froude number, which is the ratio of inertia to gravity forces. If you match the Froude number for your model boat in a test tank, you can be confident the wave patterns will be similar to the real ship.
And for something really fast where the fluid starts to compress?
Then the Mach number is king. It's the ratio of the fluid's velocity to the speed of sound. Subsonic is Mach less than 1. Supersonic is greater than 1. For any high-speed design, Mach number is critical.
And Ernst Mach, the man it's named after, actually used these ideas to solve a really interesting military mystery.
He did. Back in the 19th century, artillerymen noticed that for very high-speed shells, they'd hear 2 bangs downrange, not just 1.
2 bangs? Why?
Mach figured it out. The first bang was the muzzle blast. The second bang was the shock wave, the sonic boom, created by the shell itself traveling faster than sound.
That's incredible. And he also solved another kind of a gruesome mystery.
Yes, during the Franco-Prussian War, the French were being accused of using illegal explosive bullets because of the horrific wounds they caused.
But they weren't.
No, Mach proved it was just physics. The highly pressurized airways, the bow shock in front of the high-speed bullet, was causing the massive tissue damage before the bullet even hit. Pure fluid dynamics.
It's amazing. Okay, let's bring this back from shockwaves to a more day-to-day engineering problem, getting fluid through a pipe without losing all your pressure.
A bread and butter task. And for laminar flow, we have a wonderfully useful formula, the Hagen-Poiseuille equation. It gives you the exact pressure drop in a pipe based on flow rate, fluid viscosity, and the pipe's dimensions.
And what's the killer takeaway from that formula for a designer?
It's the diameter. The pressure drop is inversely proportional to the diameter to the fourth power.
The fourth power, so a small change makes a huge difference.
A massive difference. If you double your pipe diameter, you cut your pressure loss by a factor of 16. It's a huge lever for designing efficient systems.
And what about calculating the actual force the fluid exerts, like on a pipe bend or a turbine blade?
For that, we use the principle of conservation of momentum. You draw a control volume around your object and calculate the net change in momentum of the fluid flowing through it. That change in momentum is equal to the force exerted on the object.
Very cool. Let's wrap up the applications with efficiency. Let's talk about a diffuser, a component that's designed to slow flow down and recover pressure.
Diffusers are critical in things like jet engines. And your first instinct might be that inefficiency comes from, just friction, viscous losses inside.
Yeah.
But the research actually shows something different. The biggest killer of performance is often insufficient flow diffusion. And the cause of that is the boundary layer at the inlet getting too thick.
So it's not the friction inside the diffuser, it's the quality of the flow you feed into it that matters most.
Precisely. If you have a thick, unhealthy boundary layer coming in, one that's close to separating from the wall, the diffuser just can't do its job of recovering pressure effectively. The initial state of the flow almost predetermines the outcome.
What a journey. We've gone from ancient Roman aqueducts and Da Vinci's sketches all the way to the nonlinear complexity of Navier-Stokes.
And the power of the Reynolds number to help us simplify that chaos.
Right. We've seen how it dictates whether flow is smooth and laminar or costly and turbulent, and how this tiny boundary layer right at the wall really ends up controlling the performance of the entire system.
Which leaves us with a final provocative thought for you to consider. If the thickening of the inlet boundary layer is the primary cause of poor performance in a diffuser, how fundamentally does the initial state of the fluid, its existing turbulent structure, constrain the efficiency of the entire system before the fluid even enters the component?
That is a powerful question to end on. Thank you for joining us for this deep dive. And if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple by Strike Vision Studio, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use.